Welcome to part 4 of our Java Collections Mastery series. Today we are exploring one of the most important tools for concurrent programming, blocking queue implementations. We'll cover linked blocking queue, array blocking queue, priority blocking queue, and synchronous queue, and see how they enable robust producer consumer patterns. Understanding these queues is essential for building scalable thread-safe systems that coordinate work between threads efficiently. Let's begin by understanding what makes these queues special. Before we dive into blocking queues, let's revisit the basic queue implementation. A queue is a collection designed for holding elements prior to processing. It follows FIFO principle, first in, first out. Think of it like a line at a coffee shop. The first person in line gets served first. The basic queue interface provides operations like offer to add elements, pull to remove elements, and pick to examine the front element without removing it. However, basic queues have limitations in concurrent scenarios. In multi-thread applications, basic queue implementations face significant challenges. When a consumer thread tries to take an element from an empty queue, what should happen? It could return null or throw an exception, but then the thread would need to constantly check the queue in a loop, wasting CPU cycles. Similarly, when a producer tries to add to a full queue, it faces the same dilemma. This is where blocking queue comes to the rescue with its elegant solution. Let's explore what makes blocking queue different. Blocking queue extends queue interface with operations that wait for the queue to become non-empty when retrieving an element and wait for the space to become available when storing an element. This is a game changer for concurrent programming. Instead of busy waiting or complicated synchronization, threads can simply block efficiently until conditions are right. The blocking behavior is built into the data structure, making producer consumer patterns much simpler to implement. Now, let's examine the first and most commonly used implementation. It is a versatile, optionally bounded first in first out blocking queue based on linked nodes. Its default choice for many producer consumer scenarios and is used internally by Java's Executor framework. The linked part refers to its internal structure. It stores element in node objects linked together similar to linked list. This design allows it to efficiently handle both bounded and unbounded scenarios. Let's look at its internal architecture. Linked blocking queue uses clever two-log design to maximize throughput. It has separate logs for put operation and take operation. This means producer can add element concurrently with consumers removing the elements with minimal contention. Each element is stored in a node object containing the item and reference to the next node. This linked structure makes it naturally unbounded, though you can optionally specify a maximum capacity. Here is how to use linked blocking queue in practice. Linked blocking queue can be created as either bounded or unbounded. The bounded version helps prevent memory issues by limiting growth, while the unbounded version provides maximum flexibility. And basic operations like put method, it blocks if queue is full. Take method, it blocks if queue is empty. Offer, it returns false if queue is full. Pick method returns null if queue is empty. Now let's look at a more memory efficient alternative, array blocking queue. It is a bounded first in first out blocking queue backed by fixed size array. Unlike linked blocking queue's dynamic node based structure, array blocking queue uses a circular array or a ring buffer. This makes it more memory efficient because it allocates all needed memory upfront and has better cache locality due to elements being stored contiguously in memory. Let's examine its internal workings. Array blocking queue implements a classic ring buffer using fixed size array with two indices. Take index for the next element to remove and put index for the next slot to insert into. When either of index reaches the end of the array, it wraps around to the beginning. This circular design efficiently reuses memory. However, unlike linked blocking queue's two-lock design, array blocking queue uses single reentrant lock for all operations. The single reentrant lock ensures mutual exclusion. Only one thread can modify or inspect the queue at a time, which can limit throughput because producers and consumers cannot operate truly in parallel since both must acquire the same lock. Here is array blocking queue in action. Array blocking queue requires specifying a fixed size at construction time. This fixed size acts as a natural back pressure mechanism. When the queue is full, producers must wait, preventing memory issues and forcing system components to operate at sustainable rate. Operations behave similar to the link blocking queue. Put method blocks if queue is full, take method blocks if queue is empty. Now let's explore a queue with different ordering semantics. Priority blocking queue. It is an unbounded blocking queue that orders elements according to their natural ordering or by comparator providing at a construction time. Unlike the first in first out ordering of other blocking queues, priority blocking queue processes elements based on priority. This makes it ideal for scenarios where some tasks are more urgent than others, like emergency message handling or task scheduling systems. Let's understand its internal data structure. Priority blocking queue uses binary heap data structure, which is efficiently represented as an array. The heap property ensures that the highest priority element, according to the specified ordering, is always at the root. When you add or remove elements, the heap adjusts itself to maintain this property. The array grows automatically as needed, similar to ArrayList. This design provides O of log n time for insertions and removals, which is slightly slower than O of 1 operations of other blocking queues but necessary for maintaining priority ordering. Here is how to use priority blocking queue. With priority blocking queue, you can specify a custom comparator or rely on natural ordering for comparable objects. This queue is unbounded, so it will grow as needed, but this also means you need to be mindful of memory usage. Tasks will be processed in priority order and not in insertion order. The emergency task will be taken first, then high, and then normal. Now let's examine the most unique blocking queue. Synchronous queue. It is a spatial blocking queue with zero capacity. It doesn't store any elements internally. Instead, each insert operation must wait for corresponding remove operation by another thread and vice versa. Think of it as a direct handoff mechanism. One thread hands an element directly to another thread with no buffering in between. This makes tight coupling between producers and consumers. Let's understand its two mode of operation. Synchronous queue can operate in two mode, fair mode and unfair mode. In fair mode, it uses first in first out queue to maintain ordering, ensuring that the longest waiting thread gets served first. Internally, it uses queue based transfer mechanism. In unfair mode, it uses last in first out stack, which can provide better throughput but may lead to thread starvation. Internally, it uses a stack based transfer mechanism. The choice depends on whether you prioritize fairness or performance in your application. Here is synchronous queue in practice. Synchronous queue is fundamentally different from other blocking queues. It has no storage capacity, so isEmpty method always returns true, size method always returns 0, and pick method always returns null. It's purely a synchronization mechanism for direct handoff between threads. So here is synchronous queue in fair mode. Here is synchronous queue in unfair mode, which is default. Producer blocks until consumer takes the element, and consumer blocks until producer offers an element. Now let's discuss a critical aspect of blocking operations. All blocking operations in blocking queue can throw interrupted exception. This occurs when a thread is waiting on a put method or a take method and another thread interrupts it using the interrupt method. Proper handling of interrupted exception is crucial for responsive applications that need to support cancellation and shutdown. Let's examine the correct way to handle interruptions. When blocking operation is interrupted, you have two responsibilities. First, to clean up any resource if needed, and second, to preserve the interruption status so that code higher up the call stack knows the thread was interrupted. The standard pattern is to catch the interrupted exception, perform any necessary cleanup, and then either reinterrupt the thread or propagate the exception. And here is the wrong way to handle interrupted exception by just solving the interruption. Now let's see how these queues enable the producer consumer pattern. The producer consumer pattern is a classic concurrency design pattern where one or more producer threads generate the data or tasks and one or more consumer threads process that data or task. The pattern decouples producers from consumers, allowing them to operate at different rates. The queue acts as a buffer between them, smoothing out fluctuations in production and consumption rates. This pattern is everywhere in computing, from web servers handling requests to background job processing systems. Let's implement a basic producer consumer system. Here is a complete producer and consumer implementation using linked blocking queue. The producer generates the data and consumer process that data. The queue handles all the synchronization automatically. Producers block when the queue is full and consumer block when the queue is empty. Linked blocking queue is designed as a reliable blocking queue for traditional producer consumer patterns. Think of it as a well organized factory assembly line with controlled entry and exit points. But what if you have extremely high concurrency with many threads? If that's the scenario, consider concurrent linked queue. Concurrent linked queue takes a completely different approach. It's designed for maximum throughput in high concurrency scenarios using log free algorithms. Think of it as a high speed conveyor belt in a sorting facility. Items come in rapidly from multiple sources, get processed quickly, and move out just as fast. There is no waiting at the entrance or exit. If the belt is full, items simply can't be added until space clears naturally. Let's look under the hood at its lock-free design. Concurrent linked queue implements the Michael and Scott non-blocking queue algorithm, one of the classic lock-free data structures. Instead of using locks, it relies on atomic compare and swap operations in the head and tail pointers. When thread wants to add or remove an element, it uses CAS to attempt the modification. If another thread modifies the queue at the same moment, the CAS fails and the thread retries. This eliminates lock contention entirely. Here is how to use concurrent linked queue. Concurrent linked queue is the speed demon when performance is critical. The offer method always returns immediately, either successfully adding the item or returning false if it couldn't. Though with unbounded capacity, it essentially always succeeds. The poll method returns immediately, either with an element or null if the queue is empty. Now let's examine timeout strategies. In real world systems, indefinite blocking can be problematic. For example, web server waiting for work shouldn't be blocked forever. Blocking queue provides timed versions of offer and poll method that wait only for specified time before returning. This allows you to build responsive systems that can handle timeouts gracefully. Here, with this offer method, you wait up to 5 seconds to add item. And with this poll method, you need to wait to 10 seconds for an item. Now, let's discuss some critical best practices. First, always handle interrupted exception properly by restoring the interrupt status. Second, use bounded queues in production to prevent memory exhaustion from queue growth. Third, monitor queue sizes in production systems to detect bottlenecks. And fourth, choose right queue capacity. Choosing the right queue capacity involves balancing multiple factors. Too, too small capacity causes frequent blocking and underutilization of resources. Too large capacity wastes memory and can mask performance issues. A good starting point is to base capacity on your expected burst size. How many items might arrive faster than they can be processed during peak load? That's the burst size. Monitor your queues in production and adjust based on your actual usage patterns. Finally, let's review key takeaways. Blocking queue implementations provide powerful tools for building concurrent systems. Linked blocking queue offers general purpose first in first out queuing with optional bounds, and you can use concurrent linked queue if you need lock free algorithms to provide maximum throughput under high concurrency. Array blocking queue provides memory efficient fixed size buffering with natural back pressure. Priority blocking queue enables priority based processing for scenarios where all work is not equally important. And last, synchronous queue facilitates direct handoff between threads with no buffering. Proper interrupt handling, graceful shutdown patterns, and thoughtful capacity planning are essential for production systems. By choosing the right queue for your specific needs and following best practices, you can build robust, scalable concurrent applications that efficiently coordinate work between threads. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.